Okay, Marco, the floor is.
So, hi everyone. Should I use the microphone? Yeah, the best. I didn't intend to use this today. I wanted to do then around with some market stuff. But I realized yesterday that wasn't a good idea, so changing my mind and I prepared like 1 billion slides. I'm not even over. It's going to rush up here in slides. This is not even a paper, it's a project I've been working in the last few years. And I've been working on this stuff along with other people. Oriol is one of them. Eduardo will be one of them in the next few weeks. And the idea is to create an input-output model for the Italian economy, not because I'm interested in the Italian economy, but because I'm interested in input-output software consistent models. And why? Well, you know that ecological macroeconomics have big roots, and you know also that the early SFC models didn't used to include the ecosystem. Jahowever, this gap was closed, or starting being closed in the late 2010s, thanks to the Jacksons and Victor and Yanis and Maria who are here. And the reason is that the ecological SFC models integrate monetary stocks and flows. They are also allowing integrating physical stocks, funds, and flows. And since then, several ecological SFC models have been developed. And these models ensure consistency across economic stocks and flows and environmental stocks, funds, and flows. So they are widely used to simulate dynamic transitions, to test policy scenarios, and analyze economic environment feedbacks, all things that you know. Now, the problem is that these models, even the ecological SFC models, have limitations. And the main limitation is the very high level of aggregation of the models. While we need industry details to study the interaction between the environment and the economy. So for many environmental applications, SFC models alone are not enough, and we need hybrid IO-SFC models, which in principle could deliver industrial granularity, but also dynamic and financial coherence, which is the feature of the SFC models. So many of us, including Hart and O'Neill, and then also José Ferreiro, Oriol, and I, and Andrea, and other people that have published papers telling people, look, we need IO-SFC models. The problem with IO-SFC models is that nobody knows what we need for IO-SFC model. Nobody knows how to do it. So, despite this growing interest, just a few prototype IO-SFC models are there. There are probably other papers. I guess there's a working paper from Valdecantos, if I'm not wrong. You had a paper on IO-SFC models. Also, perhaps Gennaro and Francisco had a working paper. Not wrong about that. Perhaps Lorenzo had another paper. But anyway, I found all the various, all this like famous, then there is a recent paper by many. Then there's the two Jacksons, Beckner, Roberto, they published last year. Thompson and Foley published last year. I'm always the referee for these papers. Very well. There's the dissertation that Eduardo discussed 3 days ago, and it's an IO-SFC model. And I published myself a few things, which include some simple IO-SFC structuring there. If you download the slides, you can then click here and be redirected to my GitHub repository when you can find the code. There are also explanations on how to use it for recreating these models. And the reason why nobody knows how to develop an IO-SFC model is that there is a quite high complexity. It's not easy to integrate the two accountings. It's not easy to integrate the two philosophies, which are radically different. After all, IO models were born in a world in which we intended to plan the economy. So they are very good for those things, but they are less good for, analyzing a dynamic system. SFC models are good for analyzing a dynamic system, but as mentioned, they are fully aggregated models, and that's a major problem when it comes to analyzing the environmental economy interaction. So I've started working on this model, and I created a code which is complicated enough to allow developing an IO-SFC model for Italy, so an empirical IO-SFC model and an ecological empirical IO-SFC model, but it's simple enough, I guess, to be understood and to be used as a benchmark and to be improved in the next few years. The code produces the table, the standard table for an SFC model. For instance, the simplified balance sheet of Italy, automatically produced by the code, which produces these tables for each scenario, each period, etc. It's also a good way to double check, the entries and see if everything is right. The accounting is highly simplified compared with the standard accounting, because entries have been reclassified. You reduce the density of the matrix and therefore reduce also the complexity of the model. So this is the balance sheet, and this is the transactions flow matrix. Again, quite simple. And it's the transaction flow matrix in the case of Italy being in a steady state. So there's a further assumption in the model. There's a code forcing Italy to be in a steady state in the baseline year. This is not necessary, but has advantages when it comes to making calculations and simulation and stuff, because it keeps the model very simple and also easy to be solved. In terms of input-output accounting, you can create, and the code creates also the standard matrices. I haven't done it here because I didn't have time. But the main information that the code takes from the input-output accounting is about the technical coefficients and other coefficients we are using in the model. Anyway, if you want to see how the tables are created, you just click there here and you go redirected to a simple example of how to create an input-output SFC full set of matrices. So let's talk about the equations that are implied by the code. I wanted to show you the code actually, but so we discuss the math instead. The input-output structure of the model is quite standard. So growth output is determined based on final demands for products. Obviously, bold variables are matrices or vectors. A is the matrix of technical coefficients, X is the vector of outputs, and D is the vector of final demands. The maximum demand is then determined by using consumption from two different types of households. I have for now working class households and say capitalists and material, however you want to call them. So we have consumption, we have investments, and we have exports. And these Greek letters, so the betas, the iota, and the key there, are vectors defining the shares of, say, in the case of consumption, the share of consumption for each product, assuming that each industry is associated with a product and with a technique of production, which is obviously a simplified assumption. Notice, however, that the granularity is quite high when considering 163 industries. And C, W, C, Z, D, and X are consumption, investments, and export expressed in real terms. When I say real terms, I don't mean physical terms only. I mean, I take the nominal variable and I deflate it using an index, which I will show you later on. The way it's defined. This allows keeping. Why do I do this? Why don't I just have 163 consumption functions? Do you mean I don't want to have 163 consumption functions. I don't want to have 163 investment functions. So this seems to be a good way. It's certainly consistent. I mean, it's not consistent. It seems to be a good way to keep, the main behavioral equations constrained to have a small number of behavioral equations driving the model. Which is one of the most controversial part. Then GDP is calculated in a quite standard way, obviously subtracting imports from the demand for domestic products, from the national demand. How are prices calculated? Prices are calculated using a two-step method. In a sense, the first step is pretty much a structure-like way of defining prices. The only difference is that markups or profit rates can be different across industries. The second difference is that fixed capital depreciation is also accounted for. But this is only the first step, because there is another step. I created an algorithm, I hope it works, seems to be working, that in principle assign either either domestic prices or foreign prices to inputs, or if you like, intermediate consumption in industries, depending on whether these inputs are from other national domestic industries or foreign industries. So there is this algorithm that allows taking into consideration the fact that some of these inputs actually come from the rest of the world, and so you have to calculate that in different ways. Prices are different. Okay, this is the rest. The other thing is, how are markups defined? The markups are not fixed. The idea is to capture the effect of demand, temporary effect of demand on prices, at least in certain industries, and therefore markups increase as the gap between current outputs and potential outputs increases. However, in this model, potential outputs tends to adjust to current output. So over time, this gap is closed and markups go back to the initial state. So we have a temporary effect of demand, at least in certain industries. Obviously, these reactions, they say, elasticities are different across industries. So there are industries in which demand is very important, and other industries in which demand is not important. And that allows taking into account the effect of final demand. How are prices calculated? That, for instance, the consumer price index for the working class is just calculated by taking the bundle of consumer goods, basically the share of consumption of households, which is a vector, and multiplying it by the vector of prices. And this is done for every groups or any other sector in the economy. So I can calculate consumer price, working class consumer price index, interior class consumer price index, investment price index, and so on, which are very useful because those things allow me then to have just a few behavioral equations. In terms of income and consumption, the model is quite standard, so it's quite standard SFC model. Another possibly controversial aspect is about the investment function. So how do I have just one investment function for 163 industries? The answer is I have a target capital output ratio for each industry, and then I use it to calculate the kind of target capital stock for the economy. These target capital output ratios are different across industries, So I can calculate how much fixed capital each industry they want to have. Then they are multiplied by the respective price factors and deflated by using the investment price index. In this way, I can calculate a real target capital operation, or a real fixed capital target, and I can use it in an investment function in the standard way. So I have just one unique investment function which defines investment in real terms, which again is a trick to keep things simple, and it seems to be working. Okay, the rest is quite standard, so I don't have to discuss it. It's very, very standard and in line with the SFC literature. Even here, there's nothing controversial, I hope. And in terms of the labor market is quite simple. So the wage bill is just the number of employees per industry times the wage rates in each industry, which can be different, of course. The only big aspect perhaps I should mention is that obviously employment doesn't adjust the same speed of production. So there is some sort of hysteresis, which means that we have a coefficient, a uppercase lambda, which accounts for the fact that when production increases, we don't see a proportional increase in employment. That's it. As for the rest, it's employment is driven by the economy. Interest rate setting is quite standard again, so nothing to be said here. Taxes are quite standard. The only aspect I don't like, and I'm going to change about this model, is taxes for now are only divided on households. And I need to introduce taxes for firms. Shouldn't be too complicated, but I need that for performing future exercises. So this is the only aspect I'm sure I'm going to change in the next few weeks. But I don't expect the behavior of the model to be affected by this change. As for the government spending is based on the previous government spending plus shocks, and government spending tends to revert to a level which is in line with the European targets. So, zero deficit or whatever. Central bank is quite standard. Portfolio equations are quite standard. Export and import equations quite standard. They depend on prices, domestic prices, foreign prices, price indexes. I just introduced the line of imports to account for the so-called J-curve effect, to reimport the so-called J-curve effect. But as for the rest, there's nothing new here. Last point, which is the point I discussed yesterday with Francesco, but Francesco already found a solution, so he doesn't need this anymore. I account for the possibility that the Italian situation may affect the exchange rates. Obviously, Italy is part of the euro area, but it's a significant component of the euro area. And therefore, in this model, in principle, a big surplus or a big deficit of Italy could affect slightly the euro, depending on how we set the parameters, estimated parameters. The idea, which can be exploited for other countries, normal countries which are not the monetary union, is that the exchange rate depends on the interest rate parity condition. So interest rate must be leveled for countries, and it also depends on the expected exchange rate. And the expected exchange rate, in turn, depends on the long run exchange rate, and the long run exchange rate is the one that balance the current account balance. Okay, that's it. This way you can account for both capital flows and effects and trade effects on the exchange rate, even though in the case of Italy it's not so important. As for expectations, I assume regressive expectations because in price expectations, because in Europe we do have a clear Euro area, we do have a clear inflation target. So it makes sense to assume that the economic agents in our system behave that in the medium to long run inflation is getting back to the targeted inflation. So they are defined using a regressive mechanism. Emissions and other environmental variables are calculated in a very simple way. So by using the coefficients which can be derived from the standard data sets. The model is implemented in our environment. Equations are expressed in discrete time, and the system of difference equation is solved simultaneously using a maximum of 100 interactions per period and a quite low actually tolerance level. Each period represents 1 year. The model covers 30 periods, but I tried it for 100 periods, it works. And multidimensional matrices are used, which are perhaps the most important difference compared with other models I developed or all the authors have developed. I discovered that actually it's quite easy in R to have multidimensional matrices. It only takes you to use array. There's this command, it's quite simple. And allows you to have the same variable across different periods, different scenarios, different industries, different whatever. And the only aspect you have to be careful about when you do matrices, calculations, multiplications and stuff, you have to be careful because you are using a multidimensional object and you can get easily the calculations completely wrong. Okay. The data are derived from Eurostat and Exabase, but we are still working on that, and currently Eduardo is helping me with that. And in particular, from Exabase, we took the technical coefficients, the labor coefficients, the demand shares, the emissions coefficients, and the other variables. And then there are other coefficients, say the free parameters, which are the tools which I use to to create a baseline and to make the baseline the steady state for my economy. Okay, that's why I want to show the code. Because I do this thing, I choose a base year and then I calculate the coefficients as if in that base year the economy was in a steady state position. Why do I do that? Is that necessary? Not at all, but that makes the model much more, how can I say, it's much easier to be solved. It's quicker and it was much better than compared with other more complex algorithms. Okay, that's why I'm trying this solution here. Okay, other coefficients are taken from other works, and this is a snapshot of the base year of the model, just to see that every flows and every change in stocks has a counterpart. So I use this Sankey diagram just to give a representation of that. And obviously having a input-output structure means that basically we have a network of industries. Here I just plotted the top 12 industries. There you can see the top 70, the top 163. The problem is the picture doesn't make any sense. Okay. And then I tried a few experiments. And the experiments are, let's see how the model behaves. So first experiment is just spend some money. Just ask the government to spend, $100 billion. No targeting industries, just the spending is proportional to the size of each industry. And what you see is the economy moves as expected. Everything is adjusting as expected. The model seems to be quite stable. It's no surprise, which was just a check for me to see if everything is going the right direction. Here you can see that demand for different products moved in different ways, and we're still across output, emissions, So everything seems to work smoothly. And so after that, I tried to do something different, which is I allocate resources. I take resources from industry producing energy, renewable energy, and I put them to industries which are actually producing renewable energy. And I see what happens. So it's a say no additional deficit, almost finished. No additional deficit for the government, because I'm taking money from some industries, I'm using the same money to fund other industries. And what happens is that there is a small positive impact on the economy. The GDP is going slightly. So this redistribution has a positive effect on the economy, however small. But the interesting bit is obviously the industry which produce some of the industries which produce non-green energy obviously are shrinking, and also emissions are shrinking in those industries. At the same time, the money spent into the industries which produce green energy doesn't make them to produce more emissions. But these industries seem to be linked more with other industries in the economy, and the final result is that the overall emissions slightly increase in this experiment. This is both due to the fact that the economy is slightly growing, and to the fact that that industries producing green energy or renewable energy sources seem to be more interconnected in this industry. So the multiplying effect is higher. And therefore, we have a quite classical rebound effect in the system. So to conclude, this particular calibration method that I used, meaning to force the economy to be in the steady state in the base year, are certainly drawbacks. But it seems to be working well. It makes the model working quite smoothly. No problems. The dynamics is clear. You don't have any solving problems. Even the number of iterations which are necessary to solve the model are just a few. So it works well. So it's a good alternative compared with more complex algorithms. Obviously, you have to double check everything, particularly the data which I'm using. And for the early experiments, the key message is that every green policy is driven by some state demand or even subsidies, and those subsidies are characterized by a lower multiplying effect, seem to face a quite obvious rebound effect over time. So these are the early experiments. But for now, the model is not useful as a model for Italy. It's more useful as a model per se, as a kind of benchmark to see how these things can be done, or a benchmark for you to criticize it and tell me how I should be doing those things, because I don't know. Okay, so thank you for your attention. And
This one, just one more.